Hi everyone, welcome you all to Deep Matrix. In today's video, we are going to see about what is sampling theorem and we are going to analyze how the sampling theorem works. So in signal processing, sampling theorem states that if the sampling frequency of the continuous time signal is greater than or equal to twice the maximum frequency of the continuous signal, then we can easily reconstruct the uh, input signal from the discrete output one. For example, x of at, so this is my input signal, you can see, which is in red color, and it is continuous too, and this is a impulse function. Those who know signals and systems, you definitely know about what an impulse function is. It contain arrows which are moving towards infinity, so the impulse train would look like this when the sampler contain this impulse train. So when an input signal is get multiplied with the impulse train, we get a signal like these blue arrows. You can see the blue arrows are adjusted to the input signal which we have given. The theorem states that if we have these are nothing but samples, these arrows are nothing but samples. The theorem states that if we have these samples which should be twice the maximum frequency of the input signal, let's consider the frequency of the signal be 2. So my f of s, which is the frequency of these blue arrows, should be twice the maximum frequency. Say here we already said that 2, so 2 2s are 4, so the sampling frequency of these blue arrows should be greater than or equal to 4. It should be 4 or it should be greater than 4. In that circumstances only we can easily reconstruct this signal from these samples. So this is what sampling theorem explains. So I also explain you with the example. Sorry, wait one second. Let me choose my brush, orange color. Let's consider this is our sine wave. So it don't look like sine, but for example, just consider this as my sine wave. I'll show you two more diagrams. This diagram is one with less number of samples, and here is a signal with more number of samples. As you can see, the signal with less number of samples, it is similar to sine wave, but it is not exactly the sine wave which I have given as an input. But see here, this impulse train has a more number of samples, so that these samples, when you look from distant, you can easily identify that it is a sine wave because it contains more number of samples. So sampling theorem states that if you have more number of samples, the sampling rate should be twice the greater than of maximum frequency of the input signal. So we can easily reconstruct this sine wave from this output discrete signal. So let me join. Wait, we'll use some light color. So I'm joining the points. This is more similar to the input signal which we have given, but let me draw here. This would be similar to a sine wave, but not exactly a sine wave. Here you can see lot of clipper here because the part is clipped, since we have less number of samples. So the second part is more like a triangle wave. This is what theorem explains. If we have more number of samples, we can easily reconstruct the input signal from the discrete output signal after sampling. So here I have show you a demo with. So let me declare my f of s, my sampling frequency be 10. We all know that time period is the inverse of the frequency, so sampling time is equal to 1 by f of s, which is nothing but inverse of the sampling frequency. Here is my dt, or we can also called as x, time data. I started from the value 0 with a step size of t of s. If f of s is 10, means then t of s is obviously 0.1. From the value of 0, I am moving at a step size of 0.1 up to 2 for 2 seconds. I am going to generate a number of signals or number of samples. Next, this is my frequency, the frequency of the input which I am going to given to the sine wave. So y equal to 10. 10 is nothing but amplitude. 10 multiplied by sine of 2 pi f1 into dt. Dt is nothing but the number of samples we have in the input, or here we also declare it as x. F1 is the frequency. The output signal would contain pi frequency for 1 second, which is nothing but it contains 5 cycles. Pi is for the upper and lower cycles, and 2 is the which is a parameter we have to given to the sine. So here I have plotted x and y, and this r indicate the plot would be in red color. So we'll run this. Before that, I want to show you what is the value of x. So x is undefined. We'll run this. So now you can see my frequency is 5 and my sampling frequency is 10, but you can easily see that f of s is twice of f of 1. Here f of maximum frequency is 5, f of s is 2 times of 5 is 10. But also the output is not more like a sine wave, it is more like a triangle wave with lots of ups and down. So we have to increase the value of f of s. We'll change it to 20. So it is more like spikes of up and down, but it is it attains the pattern of sine wave. Now we'll change the value by 5. 25. We'll run again. So it is it has some few modification from the previous one. We'll run again. We'll give 50. It's not 5, 50. So it is I mean, by increasing the value of f of s, we are getting more improvement in our sine wave. It has the clipped edges on the top and bottom. So if it has a curvy structure, then we can say that it was a sine wave. Will increase now by 100. So 100. So this is exactly a sine wave which we want as a output. You can also magnify it. Wait 1 second. So this is a sine wave which we got as an output. Now let me show you with another example. In this we are going to convert this r to dot. So my sampling frequency be 10. Now we run this. So we generated our output. Here you can see the sampling points. As I mentioned before, the frequency is 10, so for 1 second it contains 10 samples. We have plotted it for 2 seconds. Here you can see 2. So here we got 20 points. While connecting these points, we get a signal which is not similar to a sine wave, but we get a signal as an output. We'll connect this now with red. So when we connect all those blue points, you get a output like this. So this is the output which we get at first. Next we go for the final observation. Let's change it to 100, change it to point, so that we can see number of samples we have in the signal. So these are the points which you have got. Now you can see it contains lots of points, more like 200 points. While connecting all these 200 points, you get a sine wave. Here you can see a pattern. So it is going up, and at the top it is coming down, then it is moving up. This is how a pattern look like. We can also connect it with the help of hold off function. Hold on. Now plot x comma y comma red color. See this, before that we undock it. We'll run this now. Just watch the figure window, you can see observation. See, we are connecting these blue dots with the red line. So this is more like a sine wave, hence the sampling theorem is proven. It is also very helpful to analyze lots of signals. I hope you enjoyed this video. Do comment our videos so that we can improve our video quality. Until then, enjoy learning. Thank you.